So basically, now that I've seen the background for the STL, right? So we'll just try to take it and add it to a model. Right? So this is where I'll talk about how we can use the STL to build upon the evaluation or evaluations of the requirements on a model and do models. Yeah, so basically, what we have seen is that there have been certain software recalls in recent times, and this is again due to the requirements not getting followed. So in this example, right, the first example is of actually it's a pretty well-known example of Boeing 737 introducing the MCAS software, which basically used to change the pitch of the airplane. Okay, try to adjust it, but what it ended up doing is that it ended up taking control away from the pilot, and that is why in the system, or there were two crashes that had happened with Boeing 737. Next example is with Tesla models, which again, when they were supposed to come to a rolling stop at the four-way stops, they continued forward. So cars used to override that and keep going forward, because of which certain accidents have occurred. Similarly, there was an issue with Mitsubishi Outlander Sport, wherein, let's say, if the input of the power input was like misread or like was not received by the ECU, right, even for a second, the gear ratio was set back to 1, which, like, let's say it happened at a very high speed, is very disastrous for the car. So, and there was like many such examples that have happened in real life. So now we can just add requirements which mitigate all of these issues that come up. So in case of now, the first example is actually taken or officially taken from what the Boeing did to remove the discrepancy that had happened. So basically what they did is that there were these two AOA sensors which were there on the wheel, and MCAS system only used one of those at a time. So now what they introduce is that the MCAS now uses both the sensors, and if the difference between those two sensors is like greater than 5.5 degrees, right, it does not activate that system. So the MCAS system and the control is not taken away from the pilots. Next is the again, these were the conditions that were put on for various different examples that were talked. So now, if we were to use STL and to formulate these requirements, this now becomes pretty easy task to add these requirements. Right? So these are basically the formulations that we can use using the STL logic. Like in the first case, right? Like you can see that always from starting from 0 time going till n whatever time is there. You have to see that both the sensors have or whenever the this distance goes greater than 5.5, you do not activate it. So these the requirements get formulated pretty nicely into an STL logic. So now another thing that comes up is that STL or the values that we get are basically qualitative, right? So we get a true or false value. So in that case, what we do not understand is like how much has the model failed or how much the controllers are going out of sync. So we only get true or false values, whether they satisfy the condition or not. So in that case, right, what we want to do is that we want to add some value, a real value that tells us how good the controllers are doing or how bad they are doing. So this is where we move on to the problem of falsification and doing a quantitative analysis of how our requirements are getting evaluated. So this is where we add real values to the solutions. And what this helps us do is that now instead of just finding the true value or the false value, we have sort of a surface or an optimization problem where we can do a minimization. So yeah, so this is where the robustness comes in. Robustness is in the real values, and which basically we can see that if it is greater than 0, right, our conditions or requirements are getting satisfied. If it is less than 0, they are getting violated. And then we can just perform a simple optimization on top of it and try to find where the input is getting falsified. So next we come to the problem of how do we do this evaluation, right? So there are two ways we could go about it. We could do a verification for a model, or we could see that certain conditions are getting false or falsification. So why do we choose to do falsification? Because falsification is faster and it is less time consuming than verification. Because take a simple example of inference, right? Like let's say you have a hypothesis and a consequence. And if I have the consequent, I see that okay, consequent is false, I can go back and see that the hypothesis is false. But if I were to say that hypothesis is correct, given that the consequence is false, I cannot conclusively prove that, okay, because I've seen 10 number of consequences being true, I cannot conclusively say that the hypothesis. But the opposite can be done is that I can find one single small false or false example for consequent, I can see that hypothesis is false. That is why falsification is much more powerful than verification. And we end up saving cost in terms of computations. So this is like a brief summary of falsification and how it comes and gets or we add it to our models essentially. So we take in the input and we have the output for it. And this is the parameter that we define. So let's say we have a controller, right? Yeah. We basically have a controller that controls a car. And we want to add a simple condition saying that the car is like in its initial stage, right? Like when it's just starting, its speed cannot exceed 120 because if it were to do that, the acceleration would be high. It would end up damaging the car, right? So we see that we add in such a condition over it. And then we feed in the data. And we get certain output, seeing whatever the robustness values for each specific input. So in this case, right, So in this case, right, first example, it's like we can see that it's for the first initial time, right, the value is less than 1, right, for the speed. And so the robustness value is 4. Similarly, for a next input, the value slightly exceeds the 120, and that's why we give it a negative robustness value. So likewise, we can conclusively see that whether a system is failing or passing the test. So this was a point about scale, right? But there are times when we need something much more powerful, and that is when we add the spatial information as well, and that is when we transition from STL to an STPL project, which will be explained by them.